Welcome everyone for today's class. In this class, we are going to discuss about thermometric titrations. Usually, the thermometric titration is like volumetric titration only, but here, practically all the chemical reactions are accompanied by heat effect, and therefore, it is possible to follow the course of a reaction by observing the heat liberated. So the thermometric titration, that is, this involves the measurement of the change of temperature of a solution during titration as a function of the volume of the titrant added. Here, the change in temperature is due to heat changes during the reaction, and the endpoint in a thermometric titration is indicated by a sharp break in the temperature versus volume curve. And in this class, we are going to discuss about the thermometric titrations, introduction, instrumentation, and applications of thermometric titrations, like the titration between hydrochloric acid and sodium hydroxide and boric acid and sodium hydroxide, and the titration between calcium and magnesium ion, mixture of these two ions versus ethylene diamine tetraacetic acid, and we shall discuss about the other techniques too. Now we need to know what is thermometric titration. The thermometric titration is defined as the titration in which endpoint is determined by measuring the heat generated during chemical reactions. Here it is like volumetric titration, but here we are going to measure the heat generated during the chemical reactions. That is, this measurement involves, this titration involves the measurement of change of temperature of a solution during the titration as a function of volume of the titrant added. So therefore, we know what is thermometric titration. That is, thermometric titration, it's a titration in which endpoint is determined by measuring the heat generated during chemical reaction. And we shall see the principles involved behind thermometric titrations. In the thermometric titration, titrant is added at known constant rate to a titrant, that is analyte, until the completion of the reaction is indicated by change in temperature, and the endpoint is determined by an inflection in the curve generated by the output of a temperature measuring device. So that is the principles involved in thermometric titration is, in this titration, the measurement of the change of temperature of a solution during titration as a function of the volume of the titrant is added, and the change in temperature is due to the heat changes during the reaction is happened. So the endpoint in this thermometric titration is indicated by the sharp break in the temperature versus volume curve. And the thermometric titrations are carried out in adiabatic conditions uh, to maximize the heat exchange between the system and the surroundings. That means this can be done in a small Dewar flask, we shall see later in instrumentation. And here the titrant titrant is added from a thermostated automated burette at a constant rate into the thermally insulated vessel that contains solution to be estimated, that is called analyte. Say for example, if we consider the titration reaction between A and B that gives the product P. Here The reaction is between A and B that gives the product P plus heat. Here A is a titrant and the small a corresponds to the number of moles of A, and B is like that only. B is analyte and small b is corresponding number of moles of B, and P is the product, and the small p is the corresponding number of moles produced, that is a product in this during the product formed in the titration. Here and this reaction, at completion of this reaction, the reaction produces a molar heat of reaction, that is change in enthalpy, which is shown as a measurable temperature change, that is change in temperature in an, if you take an ideal system, there no losses or gain of heat due to environmental influences are involved, and the progress of the reaction is observed as a constant increase or decrease of temperature depending respectively on whether uh, delta H is negative or positive. If the delta H, that is change in enthalpy, is negative, then that indicates that the reaction occurred as exothermic, and if it is positive, that is change in enthalpy is positive, then which indicates reaction as endothermic. So now we know what is thermometric titration. Now we shall see some of the conditions for thermometric titration. If we want to conduct the thermometric titration, we need to follow certain conditions. There are four conditions here given. The first one is the reaction should be um, the reaction should be accompanied by sufficient heat change that can be measured. And the second one is the heat of dilution of the product should be negligible. Third one is the reaction should be a simple one step change. If it is not a multi step changes reactions like the complex reactions, so it is unable to find, that is if the reaction is occurring in the several steps, it is impossible to determine using thermometric titrations. And the fourth one is transfer of heat between the titration vessel and its surroundings should be avoided. So we could not include the transfer of heat between the, that is system and the surroundings. So we saw there are four conditions to be followed during thermometric titration. The one is the reaction should be accompanied by the sufficient heat change that can be measured, and there must be the sufficient heat change should be happen in the reaction. And the second one is heat of dilution of the product. The product formed should be negligible. And third one is the reaction should be follow the one step change. And the fourth one, the heat change between the system and surrounding should be avoided. And here the figure shows that is thermometric titration assembly. Here we have the different parts of the instruments, and that is especially that is the motor driven burette and thermally insulated adiabatic titration vessel, that is DVAR flask, thermistor bridge setup, and recorder. So these are all the major parts in thermometric titration assembly. We shall discuss about those parts in the thermometric assembly now. So in addition to those parts in thermometric assembly, we need to add the titrant, that is here we are adding the titrant here, and so the titrant is added from here. This here we have, and this is the water jacket here we have, and this is motor stirrer. We have addition to the other parts, and this is called the thermistor. We have the thermistor. We need to connect the positive and negative terminal from here. So now we know that so what are the um, what is the assembly in thermometric titration? Here now we shall discuss about um, the instrumentation of thermometric titrations. In the instrumentation of the thermometric titrations, which consist of these are the major parts. They are motor driven burette, Devor flask, thermistor, and a recorder. So these are the major parts of instrumentation of thermometric titrations. And that I told you that the titration instrument, so which consists of motor driven, that is thermostated burette, that is motor driven thermostated burette. The motor driven thermostated burette we have here is this is the motor driven thermostated burette. Here we have, so and then in this instrument we have the thermally insulated adiabatic titration vessel, that is called Devor flask. So this is, we have the U shaped vessel, so that is called a Devor flask. This is thermally insulated adiabatic titration vessel. And we have the another major part in this. So second one is the Devor flask. So another one is thermistor bridge set. Here we have, this is called the thermistor bridge set. Here we have the positive and the negative terminal in this bridge. We shall connect this into the recorder. What changes occurring in due to the reaction. And then we have the another one is, though it will be recorded by the recorder. So these are the major parts in the instrumentation of thermometric titration. In addition to that, we need to keep this setup in the empty beaker. This is empty beaker we have. So we kept all this setup in the empty beaker, and we have stirrer. So when during the reaction we need to use the stirrer, and we kept the stirrer here. So this is called the stirrer, and we need to add the titrant. The titrant is added through this I mean, this is the burette, thermostated burette, and here we have the water jacket. We have that to control the temperature of the titrant. We have the water jacket in the instrument. So in addition to that, we have the thermometer here. This is thermometer. So here that is a known volume of the solution is to be estimated as taken in the Devor flask, and then the tip of the burette is dipped into the solution in the vessel. The vessel is covered by a thick insulated material containing holes for inserting the thermistor, and then the burette and the stirrer should be connected with this, and the titrant is added at a constant rate while the solution in the Devor flask is constantly stirred. For that we are using a stirrer here, and the thermistor uh, assembly is connected to a one arm of a wheat stone bridge. That is, here we have the positive and negative terminals. So and its resistance is recorded directly on the recorder. So this resistance is recorded through the recorder directly, and then the temperature measuring thermistor unit should be capable of measuring the temperature change of so here it can measure the temperature range of 0.01 degree Celsius, that is 0.01 degree Celsius range. So the titrant should be 10 to 100 times more concentrated than the solution in the DVAR flask, so that the titration can be done by the addition of small quantity of the titrant. So if you take the daily, the titrant, the concentration of the titrant is 10 to 100 times more concentrated than the solution in the DVAR flask, so which allows that the titration can be done by the addition of a small quantity of the titrant. So we can use the small quantity of titrant if you use this much of concentration. And so this is the schematic representation of thermometric titration. And here we have this is actual instrumentation setup of thermometric titration. Here it has the major parts it is able to see. Here also, in addition to this, so recording and plotting of the graph, we have the system, that is the computer. And so already we know that here the major parts and this, that is in titration instrument, is motor driven thermostated burette, and the another one is a DVAR flask, thermistor bridge, and recorder are given in this schematic represent. This is the setup of uh, the thermometric titration, instrumentation. So now we understood how the thermometric instrumentation works, and so, and also we know the what is thermometric titration and what the principle is behind in thermometric titration. And we know, so we understood that um, how the setup of the thermometric titration, how the thermometric instrumentation works. So everything we understood. So now we shall discuss some of the applications of thermometric titrations. So we are going to, in this we are going to discuss some of the applications of thermometric titrations. One is the titration between hydrochloric acid and sodium hydroxide, and the titration between boric acid and sodium hydroxide, and another one is the titration of the calcium and magnesium between with ethylene diamine tetraacetic acid. So first we shall take titration between hydrochloric acid and sodium hydroxide. So we know that it is a normal volume, so we can find and also we can analyze using normal volumetric titrations. We can analyze by using thermometric titration also. Here it is figure shows that the plant obtained in the thermometric titration between HCl and NaOH. पानी होना पीले को सोता के नहीं क्लास पढ़ला खातो हाँ. So here in the titration between the hydrochloric acid and sodium hydroxide, here we are taking that as a known volume of hydrochloric acid to be estimated as taken in the DVAR flask, and then the titrant, that is sodium hydroxide solution, is added from the burette. And the burette, and the temperature is recorded for the different volumes by using recorder, and according to the volume of the titrant added, and the plot of the thermogram is between the temperature and the volume of the titrant added is plotted. Here the neutralization point is indicated by the sharp inflection point, that is here we have this is the sharp inflection point, and A to B, here the little changes, and this is called the sharp. After that we have the reactions. Here we have the complete reactions, and this indicates that this equivalence point indicates that the endpoint. So by using this endpoint, we can calculate the volume of sodium hydroxide from this plot. By using the volume of NaOH needed to titrate or to neutralize the hydrochloric acid, from that volume we can calculate the concentration of the hydrochloric acid needed for the uh, hydrochloric acid. How much of the NaOH needed to titrate against HCl, and how much volume as needed for this particular temperature changes. And here is the heat of neutralization of a fully dissociated acid with a fully dissociated base is approximately the minus 56 kilojoule per mole. And we shall take another example as between the titration between boric acid and sodium hydroxide. It also the same trend is followed in here. This is also called as the thermometric titrimetry. It is the boric acid versus the sodium hydroxide titration is the one of the few methods of the titration, but it is not based on solely on consideration of the free energy change, that is delta G, and and hence on the equilibrium constant of the reaction. So that is here this titration between the boric acid versus NaOHs, so not based on the change of the free energy, so that here the change in enthalpy is measured and not be able to measure the change in free energy, that is not delta G is measured in this method. So hence this titration may give useful results even when delta G is 0 or positive. So here we have taken the example, that is boric acid versus NaOH. In this neutralization reaction, that is the change in free energy of the boric acid is minus 6.5 kilocalorie per mole. So actually here the reaction between this is boric acid, the formula for the boric acid is H3BO3. so this reacts with OH minus in the base, and it gives the negative part of H2BO3 minus. So for this titration, the boric acid and the boric acid and the sodium hydroxide here, which cannot be successfully done by any method that depends on the pH thermometric titration method. Here this thermometric titration method is successfully adopted for this type of titration. The plot here the plot shows that the thermogram of the titration between the boric acid and sodium hydroxide. So here the boric acid we could not measure by using we could not measure the endpoint of this titration using the other titrimetric analysis, but it is successfully adopted for the thermometric titration. And another one application of thermometric titration is here the titration of that is the titration between the mixture of calcium and magnesium with EDTA. Here in this titration, here in the titration of calcium and magnesium with EDTA, the stability constants of the chelates differ by less than 2 orders of magnitudes, so that the titration based on indicator can give only the sum of two ions. However, for the reaction of magnesium with EDTA, the enthalpy is the enthalpy change or the enthalpy is plus 5.5 kilocalorie per mole, whereas that for the calcium ion reaction is minus 5.7, that is 23.4 kilojoule per mole. In for magnesium it is 5.5 kilocalorie per mole, that is plus 20.1 kilojoule per mole. This distinct difference in the change in enthalpy values makes it possible for the adaptation of thermometric titration. So for estimating these two ions, so if we do the thermometric titration, it is possible to analyze or to identify the concentration or to determine the concentration of uh, these ions. Here the thermogram obtained for this titration is given here in the figure. In this figure, the titration curve for this mixture is shown in the figure. The titration was started at point A. Here the titration starting at the point A. This point A and and showed a calcium endpoint extrapolated to the B. So if we go here, we are getting the point B. We are getting the equivalent points of calcium at the point B, that is from A to B we are getting the B, and for magnesium we are getting the endpoint at C here. So if we extrapolate it, if we extrapolate like this, we are getting the endpoint for the calcium, and if we extrapolate like this, and we are getting the endpoint for the magnesium here. So like this only we can calculate. And we have the another point, the point C to D here we have is that that represents the excess reagent we are adding, that gives the change in the temperature of the excess reagents added. So by using the thermometric titration we can calculate the mixture of the concentration of the mixture of the calcium and magnesium also by using EDTA as a titrant. And we have some more applications, some applications of thermometric analysis. They are here already we know that. So that includes the neutralization of both strong and weak acids, precipitation reactions, that is neutralization between acid base titrations, precipitation titrations, redox titrations, and complex formation titration, that is complexometric titrations. So this titration can be carried out in aqueous or non-aqueous mediums also. And besides, in water titration have been reported in acidic acid, carbon tetrachloride, benzene, and nitrobenzene. Here, the precision of the thermometric titration is usually plus or minus 1%. So that it is very useful types of titration to analyze the concentration of the ions present in the solution. So and we shall see some of the some other applications of thermometric titrations. Thank you.